Hello and welcome. Today I'm going to talk about GNSS positioning methods. We know that for determining coordinates for an unknown point, we need some known points and we have to measure some quantities between these known points and the unknown points to determine the coordinates for the unknown points. In GNSS, these known points are the satellites. In fact, the coordinates of the satellites are already known. But how these coordinates are computed? In fact, we have some points at the surface of the Earth, and we have already determined their coordinate with other methods, other geodesic methods, and by some measurements between the points and the satellite, we can determine the coordinates of the satellite. That's the principle. And in that case, we say that the satellites are targets or known points. The GNSS satellites send signals and their coordinates continuously down to the surface of the Earth. And we at the surface of the Earth receive the signal, and by the signal and some measurements between the receiver and satellite, we can determine the coordinates of the receiver. As I explained, GNSS satellites are target. They are known points, and they send signals and information to receivers, which are unknown points. And we need to do some measurements between them. But what are these measurements? In all geodetic or GNSS systems, like GPS, GLONASS, Galileo, Beidou, and EGNOS, we have these three types of measurement: code measurements, carrier phase measurements, and Doppler shift. Here in this presentation, I just discussed code and carrier phase measurements. I explain geometry of satellite positioning. Consider a satellite moving along its orbit. And we have a receiver at the surface of the Earth. The position of the receiver can be shown by a vector, which we call position vector of the satellite, and show it by rho r. R means receiver. And the satellite position can also be shown by a position vector, which we show it by rho s. And the distance between the satellite and receiver by rho. So this distance, which is measured between the satellite and the receiver, is actually the norm of difference between the position vector of the satellite and receiver position vector. And based on Pythagoras' rule, we can see that this distance is related to the coordinates of the satellite and the receiver. Here, the position of the satellite, which I show them by XS, YS, and ZS, are known parameters, and the position of the coordinates of the receiver, which XR, YR, and ZR, are unknown parameters. The distance between the satellite and the receiver is actually measured based on the speed of the light and the travel time of the signal from the satellite to the receiver. So as we know in physics, by multiplying the speed of the light to time, we can get distance. That's the principle. So the principle is to determine or to measure this distance and connect this distance with the coordinates of the satellite and receiver, as you see here. As I explained before, we measure the distance between satellite and the receiver. But there is a small problem here. The clock that the satellite has is much more accurate and precise than the clock that we have as in receiver. The satellite clocks are normally atomic and much more precise and heavy. We cannot have this type of clocks which are expensive and heavy on receivers for users. This difference between the precision of the timing as satellite and precision of the timing and receiver causes that we have an error in the measured range or distance. This is why we call it pseudo-range. Pseudo-range means some range or the distance which is not really distance. It is similar to a distance. Let me show the mathematical model here. Pseudo-range is shown by R. Rho, as I already mentioned, is the true distance or true range, and delta rho is the error due to the satellite or to the receiver clock. And as we see here, this is this. And actually, but any small change in timing can lead to large changes in the pseudo range or the distance, because it is multiplied by speed of light, which is really large. So the mathematical model for the pseudo range is this one that you see here. The first thing I have already explained, and here we have another term, which is because of the low quality of the receiver clock.